let's shift our attention to Poisson distribution. In this case, we're typically going to look at n being a very large number, and p is going to be a very small number. So now we're talking about over time this is occurring. We're not talking about binomial or multinomial in this case. We're talking about something that occurs over time. This is the formula that we're going to focus on right here. And the question is, what do all those pieces mean? Well, first of all, e is a constant. Almost like pi, it has the same exact value every single time. It's a button that you can use right in your calculator. And this Greek letter gamma, I'm talking about the mean number of occurrences. So if I expect 2 to happen, that would be my mean number of occurrences. And with Poisson, we always round to 4 decimal places. So let's take a look at this formula in action. Our first example, we're talking about 350 errors in a 500-page manuscript. Well, if we had 500 errors, that would mean we'd average 1 per page. But we have less than 500 errors, so when I do a little simple division, I end up with 0.7 errors per page. And obviously we can't have 0.7 of an error per page. This is on average. So now we come back to our formula, which on the last page we saw was this. We start plugging things in. Well, I know gamma. The question is, what's my x? Well, we're looking for exactly 3 errors here. So it's going to be to the 3rd power. I put this all on my calculator. Remember, this right here is a button in your calculator, the E button, just like pi is. And when it works all out, my answer ends up being 0.0284. Let's try out one more example. Let's look at our second example here. In this case, we don't really have to do any work to get gamma because they tell us right away that on average we're talking about 3 phone calls per hour. So they're giving us that gamma is equal to 3. Well, they're asking us what's the probability that x equals 2, that we get exactly 2 phone calls. We're going to go ahead and use our formula. We're going to plug in 2 for x. If you take a second to plug that in your calculator, what you're going to realize is if we expect 3 phone calls per hour, the probability that we're only going to get 2, remember you're going to 4 decimal places, ends up being 0.2240. So about 22% of the time we'd expect that. What about at most 1 phone call? Well, at most 1 phone call, x could be 0. So we plug in 0, see what happens. And this one's a little bit different because we end up with 0 factorial in the denominator. Remember that 0 factorial does not have a value of 0. It actually, by definition, has a value of 1. So this ends up being a very small percentage of the time, but some percentage of the time nonetheless. X could also be 1, because we're talking about at most 1. No big deal. Follow the exact same logic. And they end up with a value of, I'm going to put it in my calculator. So now how do I find the probability of at least 1 phone call? I'm sorry, at most 1 phone call? Add them up. So the probability of at most 1 phone call would be those 2 numbers added together. That would be my answer to B. C says at least 3 phone calls. So in 3, we want x to be 3, 4, 5, and and so on and so forth. It does not include 0, 1, and 2, which, lucky for us, we already have. We have 0. It's right here. We have 1. And we have 2. If I take those three things and add them together, the probability that x is less than or equal to 2 is going to end up being that's the complement of what I want. Since it's the complement of what I want, just subtract it from 1. So the probability of me getting at least 3 phone calls in the hour .5766.